Aloha, this is Roger Brewer with the Hawaii Department of Health. This is a recording of a presentation I gave to the State Risk Assessor Association October 20th, 2020, entitled Untangling the PFAS Web, Perspectives on Fate, Risk, and Screening Levels from Hawaii. In Hawaii, we're just getting started with PFAS. So what I want to do today is go over some of the lessons learned, especially from the draft guidance we published in July of this year, and also talk about some of the updates that we plan to make in the near future. So in Hawaii, I think you could say we had the newcomer's advantage to PFAS. We haven't had any PFAS sites here that we really need to look at for several years. The first one came up earlier this year. It was an airport on Maui. It was a fire training area. They installed monitoring wells right within the fire training area and then also downgrading of the fire training area about 500 feet. It's right by the coast, by the ocean. There's a beach about 500 feet away. It's low risk. It's not a source of drinking water. There's some concern about potential discharge to the shoreline area from aquatic toxicity standpoints. So the questions that came up here is there one or two sources? If you look at the fire training area, then the makeup of the PFAS was pretty similar to what we saw in literature, published literature. You had PFOS 41%. There was some of the hexasulfonate and some hexacarboxylate, 22% each, and this PFBS. So a lot of acronyms we're starting to get familiar with, but it seemed pretty similar. But down in the downgrading area, it was completely different. There, the groundwater was dominated by the hexacarboxylate, this PFHXA, 41%, a lot of the PFBS, 35%. We saw some in the source area, but it was totally dominating the downgrading area. And then a lot of the hexasulfonate again, 20%. So there's a question, are we looking at one or two different source areas? And also in the literature we looked at in other states published screening levels, mostly focused on PFOS and PFOA. So it seemed real obvious here, especially in the downgraded area, that we needed action levels or screening levels for PFAS other than PFOS and PFOA. So we need to expand our action levels. Quick outline of the presentation. Very briefly go over the nature and use of PFAS. There's a lot of information about this on the web, so we won't spend much time on that. And then start working through the process we went through to develop action levels. First, look at the targeted PFAS, especially the nomenclature, which I know can be very confusing the occurrence of PFAS in different scenarios, and then laboratory analysis, how the labs are reporting these compounds. Once we identify that, then we'll look at the potential environmental concerns posed by the compounds. And then we can start thinking about development of soil and groundwater action or screening levels. And we'll go back to this fire training site case study with a new perspective on it based on what we learned from our action levels. And we'll end up looking at some looming issues, leaching of PFAS from soil, where we're comparing models versus laboratory tests. We should probably be going more toward the latter. And also wastewater, biosolids, and uptake in food crops where agricultural land has been either irrigated by treated wastewater or the soil has been amended with biosolids. Don't want to end up with I think some other problems that we've seen in the past, we've been working on for the past 15 years here, is collecting representative sample data of all these different types of media. Now my background's actually a geologist, but I like to say, forced to be trained as a risk assessor early on. It's a quote I got from a t-shirt. I kind of adapted it. It was actually for an engineer originally, but a risk assessor is someone who does precision guesswork based on unreliable data provided by those of questionable knowledge. See also wizard, magician. So my geologist side was out in the field collecting these samples and getting data and then giving it to my risk assessor side, which is wondering what to do with this data. A lot of it didn't make any sense. It was highly variable. So we'll look at that at the end of the presentation today. Quick references, the guidance we published in July, interim soil and water environmental action levels for perfluoro and polyfluoroalkyl substances, PFAS. We add the S on the end of it to make it plural. We discussed that in our memo. This will be updated in fall, probably in November or December, year 2020. And our action level guidance in general is the next document, evaluation of environmental hazards at sites with contaminated soil and groundwater. Webpage there. For a good general background on PFAS, check ITRC's 2020 document. And then Washington State Department of Ecology recently published really a detailed document on PFAS, referred to it, there's a chemical action plan. And a lot of states are publishing some really good guidance documents. We've talked to a lot of people, and really what we're doing represents a compilation of what a lot of other states are doing. We have our recorded webinars, this one, and along with a lot of others on sampling and vapor intrusion and action levels, a lot of other issues posted to our webinar webpage, and these are uploaded to YouTube. Quick review of the use of PFAS. In use since 1940s, I think everyone knows by now, it's mostly used for water and oil-resistant textiles and papers, non-stick cookware, fire suppression foams, and then various uses in industrial settings. Started to become aware of the toxicity of these compounds in the 1970s, and just now starting to look at it in more detail, especially in places like Hawaii. Very persistent in the environment, very difficult to treat. Next, let's look at the forms and nomenclature of PFAS. And this can be really overwhelming, seem very complex when you first get started. Actually, the chemistry is quite simple. These compounds are they're hydrocarbon compounds where the hydrogens that were attached to the carbons have been replaced with fluorine. We focus on the perfluoro compounds. This means that all of the hydrogen atoms have been replaced with fluorine. You also hear about polyfluorinated compounds. This is where only part of the hydrogen atoms have been replaced with fluorine. So focusing on this, the names are very simple actually. The first term is perfluoro, which means it's saturated with fluorine. The second term in the name relates to the number of carbon atoms, whether it's penta, hexa, octa, nona, such. And the last part of the name is the functional group. So looking at sulfonic acids and sulfonates. In the first case, we have perfluorooctane sulfonic acid, PFOS. Now, when this compound is found in the environment or mixed with water, then the hydrogen atom dissociates. You end up with perfluorooctane sulfonate. Again, PFOS, you'll see the little negative sign we include in the abbreviation to indicate that it's an anion. It's fairly simple. So that's the first set of compounds, these sulfonic acids and sulfonates. The second set of compounds we focus on are carboxylic acids and carboxylates, which just means you have a extra carbon molecule instead of a sulfur. So we have perfluorooctanoic acid, PFOA. We have perfluorooctanoate when the hydrogen atom has been lost. There are also lots of other compounds. We're just focusing on the ones above for now. And there's a lot of PFAS precursors. So these are the polyfluoro compounds that can break down into these refer to as terminal end products, the perfluoro compounds. That's the general groups of PFAS. So now we need to get more specific. What are the actual targeted PFAS we should be looking at in the environment? So we have these two groups. We have the protonated or the hydrogen acids versus the anions. Some laboratory chemists reminded me that some of the anions are actually acids. That's why you'll see us use the term protonated or the H positive acids to refer to the compounds we're talking about. This is where it started getting confusing. So we were looking at the ITRC's document and along with other documents, and they state most PFAS are present in the environment in human matrices in their anionic form. And here they're referring to these perfluoro compounds. That's okay, that's simple enough. So they've lost that hydrogen atom. Although laboratories may be reporting the protonated acid form of the name, they're actually measuring the anionic form. Well, this gets odd. If it's all the anion form, then why are they reporting the acid forms? And then especially the last part, physical and chemical properties of protonated acid versus anion forms are different, and it is important to know which form is present in the environment when attempting to explain environmental behavior through mathematical fate and transport modeling, where they're talking about risk assessment and the development of screening levels and such. So there's some kind of odd conflict between how the lab's reporting the data and what's in the field and what we need to be focusing on for risk assessment. We talk to a lot of laboratories and say, well, why are you doing this? If it's all anionic form in the field or in the environment, why are you reporting acids? So laboratories process samples in a manner that converts any H acid, the protonated acid forms of the compounds present, to anion forms, if they happen to be present at all, the acid forms. So the methods they use can't distinguish between protonated acid forms and the anion forms. What they report is all anion forms. As a default, the measured anion form concentration of the compounds is converted to equivalent protonated acid concentrations for the final reporting. And it's simple enough to do. You take the concentration reported for the acid, or the concentration for the acid is equal to the concentration reported for the anions times the ratio of the molecular weights, which only differs by 1 between the acid and anion form. So it doesn't really make a big difference. So we ask, why do you do this? Well, because that's what's in the US EPA lab SOPs for these laboratory methods. They list the protonated acid forms. And I couldn't find out why, but I'm guessing it's because these original lab SOPs were based on testing of the industrial chemicals, which are more likely to be in the acid forms. Well, this is inconsequential in terms of reported concentration. Doesn't make any big difference, plus or minus 0.1% or something. But it has really important implications for the accurate evaluation of fate and transport, risk assessment, risk communication, development of action levels and such. So when we first started, we heard reports talking about perfluorooctane sulfonic acid, PFOS, in drinking water. Well, now we know if someone asks the question, what is the concentration of perfluorooctane sulfonic acid in drinking water? Well, it's 0, because it could never exist in drinking water. It would always convert to the anion form. Also, the toxicity studies we started looking at were based on a mix of acid forms and anion forms. So really, we had a big case of apples and oranges here, where you compare the occurrence in nature, what's being reported by a laboratory, what's in the toxicity studies. So in your risk assessment, it's a big mix. Maybe you're getting the right answer, maybe you're not. It's something we need to look at in more detail. So we talked to a lot of people from different states and in US EPA and other experts. The first lesson learned was stick to the anions. Now in our July 2020 guidance, we list the acid forms of these compounds. That was a mistake. We should have been listing the anion forms, the sulfonates and the carboxylates, because that's what we find in nature. And the one thing we did, I mentioned before, they use the same acronym, the same abbreviation for the compounds in a lot of literature and EPA guidance, like perfluorooctane sulfonic acid is listed as PFOS, and they have the same abbreviation for perfluorooctane sulfonate. Well, that gets really confusing. So in our updated guidance, which should come out in November, December this year, we're going to add a negative sign after the abbreviation just to indicate that we're talking about the anion form. This is important because in our updated guidance, we'll use the physiochemical constants for the anion forms to develop the action levels. This can make a big difference in the fate and transport and leaching concerns and such. The anion forms tend to have a higher solubility, so maybe more mobile, lower volatility, and then the absorption can vary. And really, the absorption coefficients for these compounds are all over the place based on different types of literature. It's another issue we have to think about. We'll also, in our updated guidance, need to clarify that the toxicity factors from studies based on doses of protonated acid forms, the compounds, are also applicable to the anion forms, and vice versa. So the difference in the administered dose in these studies is really inconsequential, again, just plus or minus 0.1%. So now, once we start doing this, sticking to the anions, then we're comparing more apples to apples, the occurrence in nature, the reporting by the laboratory, the toxicity studies, and the risk assessments and development of action levels. So first lesson learned. So the next step is to identify specific PFAS compounds to target for investigation. There are hundreds of these compounds. We need to narrow it down to the ones that are of most concern in the environment. Once we do that, we can identify potential environmental concerns associated with these compounds. Then we'll start compiling physiochemical constants and toxicity factors for individual compounds, input those into fate and transport models and exposure risk models. And then we calculate action levels in soil and groundwater. We also need to compile aquatic toxicity action levels, chronic and acute, which is a big deal in areas in coastal areas and areas near rivers where the groundwater might not be a source of drinking water, but it could pose aquatic toxicity concerns. One thing to point out here in Hawaii is the action levels are optional for use. We don't promulgate our action levels or standards. We update them as needed. And alternative site-specific action levels can always be presented for review and approval. Now we're getting a little bit closer. What are the specific compounds we should be looking for? We ask a lot of people in different states what they're finding. And the laboratory methods tend to report a dozen or 2 dozen or more different compounds. Been working a lot with Matt Small and some people in California EPA. They talk about the big 9 that they're seeing in the groundwater there. You see them listed here. I won't go through those. And there's a different mix depending on whether you're looking at contamination associated with firefighting training areas or leachate from landfill or wastewater and biosolids from wastewater treatment plants. You can get the general idea from this. So one issue that's come up again is most state guidance we looked at, and EPA guidance, was focusing on the PFOS, the octane sulfonates, and the PFOA, the octane carboxylates. And we know we have all these other compounds in the water, so that's the first thing we had to jump on, is coming up with the toxicity factors and fate and transport constants for these chemicals. We know they're not the dominant PFAS at a lot of the sites we look at. So we have our list of chemicals now. We know what to call them, what form they're in. The next thing was to think about potential environmental concerns associated with these chemicals in contaminated soil and groundwater. For contaminated soil, the first 2 main issues we would look at are direct exposure, so the kids playing in the dirt, standard risk assessment, but also leaching of these compounds and impacts to groundwater. That's a huge issue at a lot of sites. At the Maui airport site, the groundwater is heavily contaminated, hundreds of ppb or ppm levels of PFAS in the groundwater. Fortunately, it's not a source of drinking water, but it could have been in another place. So direct exposure and leaching. Also, for PFAS, we're concerned about uptake into food crops and livestock feed, which our office doesn't have a lot of experience in. We're just starting to look into. Concerns associated with contaminated groundwater. The first thought is usually impacts to drinking water. Also, again, in Hawaii, we're concerned about discharge to aquatic habitats, and also the use of either contaminated groundwater through leaching or treated wastewater from wastewater treatment plants for irrigation and uptake, again, into food crops or livestock feed. So there we have our concerns. We know what we're looking for, the compounds, the specific types of environmental concerns to look at. The next thing to do is to start compiling toxicity factors and physiochemical constants. And this was challenging at first, but we found some great references. Physiochemical constants, the US EPA has I think it's called a great database for chemicals. I forget the exact name. It's in our memo. Also, the European Chemical Agency has published a lot of information on PFAS compounds. I think in general, Europe's a little bit ahead of the US on this. ITRC's has looked into this. We actually used their absorption coefficients. They were very specific there to come up with absorption coefficients that they felt were specific to the anionic forms and not the acid forms. It's very useful. The next step, really critical step, was to compile toxicity factors. Well, the US EPA has only published toxicity factors for 4 of the PFAS compounds. You see them listed there. The compounds in red are compounds where, based on our sort of cursory review of the background documents, are based on primarily the protonated acid forms of the compounds. We need to point out in our document that toxicity factors associated with these compounds are also applicable to the anion forms. So that was only 4. That's been a big problem. We need to expand it from that. Well, Michigan, Minnesota, Texas have all looked at a lot of these other compounds also. So we went through their studies and then picked toxicity factors we felt we could use here. So you see the ones listed for Michigan and Minnesota and Texas. One thing with Texas, I think because they have a lot of chemical industrial plants where they're using these raw products and they're concerned about air emissions and such, they're the only state that's published inhalation reference concentrations for PFAS. They have for 8 compounds. And we included those in our draft guidance in July, and we'll probably include them in our updated guidance also. We're still thinking about that. So now we're up to, I think, 9 compounds, which is still good, but we're still missing information for a lot of the compounds we're seeing in the field and people we talk to in California, other states are seeing in groundwater. So a great find was in Europe, the Netherlands RIVM group. If you're not familiar with them, they're kind of a great research center for environmental research in Europe. They published a document in 2018 and they published toxicity equivalent factors for, I think, 18 or or so PFAS compounds. You can see here they're all in red based on their descriptions. Their toxicity equivalency factors are all based on the acid forms, but still usable for the anion forms. This is great. Suddenly we're up to 18 different compounds where we have physiochemical constants and toxicity factors. So now we can kind of take off and start developing action levels. Like I mentioned, we also want to compile information on aquatic toxicity, where here we've had less luck. We hope to talk with other people in different states about this. We only found acute and or chronic action levels for aquatic toxicity for 5 compounds. You see them listed here. Fortunately, several states are compiling toxicity data. Washington State's just put together a great compilation of aquatic toxicity studies for PFAS compounds. I know there's some groups in US EPA doing the same thing. There's similar issues with whether studies were using protonated acid forms or anion forms, but that's definitely manageable. One issue is we don't want groundwater that's heavily contaminated with PFAS but not a source of drinking water to be forgotten about. So we use the drinking water action level as a temporary surrogate to screen groundwater even for non-drinking water areas, and then flag potential concerns. And then we'll probably for these kind of sites, we'll be focusing more on laboratory bioassay tests if you fail the action level instead of just looking at the action level. So here's our action levels. Here's the groundwater action levels. You see them listed for drinking water and then aquatic toxicity, chronic and acute. Looking at the drinking water action levels, we looked at several guidance documents and made a combination of where for the development of action levels, we use a relative source concentration of 20%. It's only 20% of the maximum daily dose we're going to assign to drinking water exposure. And a non-cancer hazard quotient of 0.5. So we're assuming there could be one other PFAS compound there that's also present at pretty high concentrations or getting close to its action level that could cause cumulative concerns. So if you look at the numbers, you see lots of zeros, looking at micrograms per liter. They're fairly familiar with PFOS. The action level is 40 parts per trillion. Same thing with PFOA, 40 parts per trillion. But look at the hexasulfonate, 19 parts per trillion. Several states have looked at toxicity studies. They all conclude pretty much the same thing. The hexasulfonate is twice as toxic as these PFOS and PFOA. So it could be present at half the concentration and pose the same risk. We then start looking at some of the other compounds, these longer chain, PFNA, PFDA, and they're even lower. It's 4 parts per trillion, the drinking water action level. Some of the compounds aren't as toxic, like the PFBS, the butane sulfonate, 40 micrograms per liter. Same thing with PFBA, the butane carboxylate, 7.6. But in general, they're all really low parts per trillion. The aquatic toxicity action levels, the few that we could find, were much higher than the action levels we came up based on drinking water toxicity. You can see them here, either a few times higher up to several orders of magnitude higher. So that's useful to know, which I think if we're screening groundwater initially based on our drinking water action levels, even if it's not a source of drinking water, it'll flag potential concerns. And then we can go on to bioassay test and see if we really do have a concern at the site. So all the numbers here in red are where we had to substitute the drinking water action level just as a temporary surrogate. That's the groundwater. Let's look at the soil next. Now these numbers I'm showing you here are draft October 2020. These are reflecting the anion physiochemical constants instead of the acid physiochemical constants like we used in July. So these are updated from the July memo. This is probably what's going to be in the memo. I need to look at them one more time. But again, look at all the zeros. If we're looking at direct exposure, you see residential and commercial industrial exposure, milligrams per kilograms. PFOS, 25 parts per billion, that's really low. PFOA, the same thing. There's your hexasulfonate, twice as toxic, half the concentration. And then you start looking at these PFNA, PFDA, these longer chain compounds. Then you're looking at single-digit part per billion concentrations, which is super low. And good luck being able to collect representative soil samples and get down that low. We'll talk about it at the end. It's very difficult. Commercial industrial action levels, fortunately, a lot higher because the residential action levels are based on childhood exposure, ages 1 through 6. Commercial industrials, adults. So a lot higher, but some of the action levels are still in the part per billion range, especially these longer chain compounds. And again, the hexasulfonates and even the heptasulfonates. Leaching the groundwater, though, look at the numbers here. I mean, they're all lower, much lower than direct exposure action levels. So in terms of risk, if you have PFAS-contaminated soil at the site, the kids could be playing in the dirt, but in theory, it could still leach out and contaminate the groundwater. So look at the action levels for PFOS. This is similar to what you're seeing in other documents. 7 parts per billion in the soil could be a potential leaching concern. PFOA is more mobile, 1 part per billion. You see some of these that heptacarboxylate, 0.3 parts per billion, 0.8, 0.5. So these are long chain numbers. These are all based on sea soil model that we use for our other compounds. The model works pretty well, I think, for solvents and things like that, but in general, we find that it's just way over conservative for compounds that can be more sorptive to soil, more difficult to desorb than the original database used to develop the model. And then some of the compounds, these longer chain compounds, the tridecacarboxylates, the tetradecacarboxylates and such, the model just completely falls apart. These compounds are highly sorptive and highly soluble, and the model will predict the action levels of 1 million parts per million, which we wouldn't believe. So in this case, you're going to have to use some kind of laboratory test. You see this action levels for non-drinking water are higher, again, reflecting higher groundwater action levels for the same compounds. And you saw the red where we had to substitute in the drinking water standard. So the leaching-based action level is the same as it is if you're dealing with soil that's over a drinking water resource. Anyway, there are our action levels, all very low for soil and water. And again, the soil, I forget if I mentioned it, action levels were again based on a relative source concentration of 20%, non-cancer hazard quotient of 0.5. So that's the action levels. We've been working a lot with Matt Small in Region 9 and again, a lot of regulators from California and other states trying to get our arms around this PFAS issue and think more about it from a broader perspective. Here we plotted toxicity on the y-axis here, increasing toward the origin, and mobility based on the sorption coefficient KOC, where the increasing mobility toward the origin too. So in the bottom right-hand corner here, we have highly toxic and highly mobile chemicals in theory. Luckily, no PFAS fall in this little box yet. In the upper right-hand corner, the green, these would be chemicals, PFAS compounds, low toxicity, low mobility. Again, nothing there. But now we can start thinking of this, I think, in terms of other compounds we're more familiar with dealing with. So let's look at these highly immobile compounds that are still highly toxic. So low mobility, high toxicity compounds. Some of these longer chain PFAS fall in this area. So these I kind of think of as like PCBs. So maybe we're going to see similar problems, plant uptake and uptake into different types of animals and such as we see with PCBs and such. You get into the middle column here, the compounds are getting more mobile. Again, the ones in the bottom here are more toxic. So you see that hexasulfonate, the heptasulfonate, and then the decacarboxylate, the nonacarboxylate, are more toxic than PFOS and PFOA and about the same mobility. So these compounds, if they're at your site, they could pose a greater risk than PFOS and PFOA. Something to think about. Then we start looking at the more mobile compounds and talking with people in other states and looking at data we see, you start seeing a lot of this butane sulfonate and butane carboxylate, and hexane carboxylate. These tend to really show up in groundwater, so we know they're more mobile. The nice thing is they're also less toxic. So that's one good point about the whole PFAS issue. So it's something useful, I think. You can look at this in a lot of other potential projects also, plant uptake and bioaccumulation and fish and such. How about this issue? Do we have one plume or two plumes? So Matt and I and others were looking at how these plumes might start to separate over time. So in this is a hypothetical PFAS groundwater plume separation, just based on sorption and mobility again, looking at KOC constant, assuming it's correct. So on the left here in the source area, let's say we dump an equal amount of all these different 18 compounds now. We have them ordered in decreasing mobility. So this HFPODA, which I haven't talked about much, is the most mobile, most soluble, or least sorptive. And then down at the very bottom, this tetradecacarboxylate is the most sorptive. So it's not going to go very far. So you'll find all these in the source area. You go immediately down gradient then, and all these compounds that are more sorptive, are going to get stuck. They're not going to be able to get out of the source area as much. So you have a different makeup in the groundwater plume as the groundwater flows through the contaminated area and moves away from the source. So a different composition here. And then when you get to the leading edge of the plume, now here you're looking at the most mobile compounds, the least sorptive, and you see the different makeup there. Now here's the hexacarboxylates, the pentacarboxylates, butane sulfonates, heptacarboxylates. So the PFBA, the butane carboxylate. So it gives you an idea now of how one source could lead to a plume of very different characteristics. That, I think, explains what we saw in Maui at the airport. And looking at a lot of data, groundwater data for people in other states, they see the same thing, this type of separation. I think now in the Maui training area, we have a fire training area, we have one plume, more than likely. Most of the PFOS, the octasulfonate, is trapped in the source area where they actually used it because it's more sorptive. Makes sense. It sticks to the organic carbon and probably the clays and such in the soil more than the others. Downgraded area is dominated by these more mobile PFAS compounds, the hexacarboxylates and the butane sulfonates. So that makes sense because they're more mobile. But the hexasulfonate is still makes up the same relative proportion in the downgraded areas it does in the source area. And based on the published sorption coefficients for hexasulfonate, it should be getting more stuck in the source area. So something's up with that. I think the hexasulfonates must be less sorptive and or more soluble than some of the studies that we were using to come up with our constants and develop action levels. Now, the groundwater at these sites, again, this particular site, it all fails aquatic toxicity action levels. I mean, it's super high here, hundreds of billions or even ppm levels of these PFAS. So the next step here was start installing monitoring wells and getting a better idea where the plume is and if it really is one single plume. But if this happened to be a source of drinking water, then definitely all the action levels for all the drinking water, all these compounds would be exceeded, including in the downgrading area, the upgrading area. So if you were dealing with the downgrading area plume and you only tested for PFOS and PFOA, it could well be, those concentrations could well be below potential action levels based on toxicity, but you still could have potential problems from the hexasulfonate and even these other compounds, even though they're less toxic overall, just a much higher concentration. So looking at that in a little more detail, here's the PFAS makeup in the fire training area. Again, dominated by PFOS, still a lot of hexasulfonate, a fair amount of the hexacarboxylate also. When you look at this in terms of risk, though, then the hexasulfonate is actually driving risk. There's twice as much for the octasulfonate, PFOS, as the hexasulfonate, but the hexasulfonate is twice as toxic. So it actually drives risks. And then these other compounds, the hexacarboxylate and butane sulfonate, there's a lot there in the groundwater, but they're not very toxic. So they don't really drive risks. So the point here is you could clean up a site and reduce the PFOS down to its action level, and you reduce the hexasulfonate the same amount. Your PFOS could meet your action levels for risk, but your hexasulfonate could still exceed action level based on toxicity. Now the downgrading area is something similar, totally dominated by the hexacarboxylates and the butane sulfonates, 75% of the PFAS there. You still have that hexasulfonate though, but if you look at this in terms of risk, then the risk is totally driven by hexasulfonate, 92% of your total risk. So there may be twice as much hexacarboxylate as the hexasulfonate, but the hexasulfonate is 200 times as toxic. So again, you have to think in terms of toxicity, not just concentration, which I know this is academic to risk assessors, but it's just something to keep reminding ourselves. So that was the main part here with our action levels. And taking a quick look now at some of these looming problems, looming issues here. First, leaching of PFAS from the soil. We use a model that I talked about, the sea soil model. We probably need to be moving on to laboratory leaching tests. Talk about that in a minute. And then next, after that, we'll take a quick look at plant uptake. And that's where we really need more field studies. And again, our office hasn't looked into this at all. So we need to chat more with people in other states. So first, the leaching. I know a lot of people don't look at this. Our office has been looking at leaching issues since I started in the mid-90s because we're an island out surrounded by an ocean of salt water. And contaminating the drinking water aquifers is a big deal. The next aquifer is about 3,000 miles away from all the other islands. So the way the model works is you input the concentration of a contaminant in the groundwater, your target drinking water action level or non-drinking water action level. The model back calculates a concentration in leachate at the groundwater interface after taking into account mixing like a 20-fold deletion of that. So this number times, say, times 20 or whatever. And then the model back calculates a concentration in the source area leachate, just looking at fate and transport properties of the chemical. And then based on the concentration of the chemical in the source area, the model back calculates an equivalent concentration in soil at equilibrium. That's how these fate and transport models work. You can see the equation here. The concentration in soil is equal to the concentration in groundwater. This is a simplified algorithm from the model. And it's just a function of the Henry's constant, which looks at the volatility of the chemical times the KOC, the sorption coefficient. Again, this works pretty well, I think, for solvents and such, probably not for PFAS. A key thing here is when you're looking at leaching concerns from soil is you need to specify specific, the targeted area and volume of soil that your action levels apply to. Because you're not going to be able to look for every drop of leachate that exceeds some action level. You have to designate a volume of soil, probably around 100 cubic yards, maybe several hundred cubic yards, and you would get the mean concentration for that soil. And that's what the action level applies to, not for every pinch of soil. So we've seen from other chemicals, especially organochlorine pesticides and metals and such, that sea soil, we don't really see from metals actually, sea soil tends to way over predict contaminant desorption and concentration in leachate for chemicals, say, other than solvents. So the action levels tend to be way too conservative. Really, once we exceed that in our guidance, then we recommend that the consultant take the same sample and run it through a synthetic precipitation leaching procedure batch test, where they put a spoonful of dirt in a liter or two of fake rainwater, shake it up for a day or so, and they compare the mass of the chemical that was originally absorbed to the soil sample data to the mass that went into the solution. And that ratio is a sorption coefficient, the KD. And then you take that KD value and you put it into an equilibrium partitioning equation and calculate a leachate concentration. A lot of people do it. It's not correct. You can't really compare the SPLP concentration directly to your groundwater action level because it's not intended to directly mimic leaching. You have to calculate the sorption coefficient. We have guidance on that. It's referenced there. Much better way to do this, I think, and especially for PFAS, is running these soil column leaching tests where you pack a column with the soil and then you pump water up through the column, and then you measure what comes out the top in the leachate. And we're still working on developing guidance for that. That's the leaching issues. Now the big bugaboo kind of the PFAS uptake into food crops and livestock feed. That's a big issue because I'll mention in a minute. For decades, biosolids from wastewater treatment plants have been added to fields to amend the fields and improve crop yield. So the question here is if PFAS-contaminated soil from these, usually from biosolids, PFAS-contaminated groundwater could be posing contamination risk to crops being grown at the same site. Let's take a look at what's in the wastewater first. And we just started doing this. This is just one reference we found to be useful. If you look at the source of the wastewater and then the total PFAS concentrations in the wastewater, we know that domestic wastewater treatment plants that primarily receive wastewater from households and such, the PFAS concentration is in comparison relatively low. And it's coming from food packaging, dust, household equipment, and such. This is in the paper referenced below. And then but looking at PFAS on an industrial setting where they're actually producing PFAS or using them very intensely in the industrial process, and then it's getting in their wastewater, PFAS concentrations can be over an order of magnitude higher. So that initially you want to focus on biosolids and wastewater from these wastewater treatment plants that are accepting wastewater from these PFAS intensive industries. And that'll help hopefully screen out different types of scenarios where we don't really need to worry about wastewater and biosolids. But that's the place to start, the worst case, and work backwards. Also, the PFAS in the wastewater, as noted here, can be dominated by all these precursor compounds, which you wouldn't see if you only tested for the 18 compounds we listed. So you really need to get a better idea of your total PFAS precursor concentrations in groundwater or in your water in the biosolids. But that's a different story. There are other groups who are looking into that now. How about in the sludge? I was in the wastewater. Sludge in the biosolids. There's something to think about. You get approximately 75 to 100 tons of wastewater sludge dry weight. These biosolids are generated per 1 million people per day. So one way to think about this, you see these dump trucks going down the road, they hold about 10 tons of whatever, of dirt and such. So about 10 of these trucks per 1 million people per day. It's the biosolids getting hauled away from these wastewater treatment plants. Well, that stuff has to go somewhere. So think about the population in your state. How many of these trucks are going down the road every day with this wastewater sludge? Something has to happen to. Well, in the U.S., about a little bit over half of the biosolids that produced in the sludge are sold as soil amendments, used as soil amendments on about 1% of the total cropland. You see the web page, we got that from there. And the nice thing is you get a significant increase in crop yield. We were talking with some folks in New Hampshire, who I think they're the experts on biosolids at the moment, dealing with crops. They say it would double your crop yield by adding biosolids to the soil. But it's a big problem because of PFAS and the biosolids and such. If the landfills quit taking it because they don't want it in their leachate, they're concerned about it, and farmers start refusing it. Well, that's a lot of trucks going down the road that have to go somewhere. Quick example makeup of the PFAS is from the New Hampshire group. You see it's a big mix, a lot of the common compounds, a lot of the acronyms or the abbreviations we see now. It's all in there, the mix. And then you see these PFAS compounds here. These are all some of the precursors, which you tend to see a lot in the wastewater and in the biosolids. So somehow we have to take those into account because these compounds could break down over time into the terminal, more toxic compounds like PFAS and hexasulfonate and such. Got to think about how to deal with that. Can these get taken up to the plants? Well, yes, they can. There's a study done by, I think it's the University of Colorado, Ray University in Colorado. It's a laboratory study where they grew strawberries and other things in biosolids amended soil. And you see the distribution here. In general, the carboxylates get taken up more than the sulfonates into the plant. The longer chain PFAS tend to accumulate in the roots, in the shoots. Shorter chain PFAS, the more soluble or the more mobile ones, tend to make it up into the fruits. So they do get into the plants. We know from some issues in Maine and other states, it's gotten up into livestock feed, hay and such at levels that definitely pose problems. In those cases, if you not familiar with it, the dairy cows were eating hay that ended up being contaminated with PFAS and it got into the milk and they had to shut the dairy farm down. So now what we really need next, and we're nowhere near close to doing this, is soil and groundwater or irrigation water action levels for plant uptake of PFAS. These will be calculated, soil and groundwater action level will be based on a function of the food action level, whatever crop we're looking at, divided by some bioaccumulation factor. The bioaccumulation factor, the way we're looking at it here, just to think about it, is the concentration of the PFAS in the plant divided by the concentration of the PFAS in the soil or in the water being used. So starting off looking at what the food action levels, those are actually a lot simpler to look at. In Hawaii, we have a default Pacific Asian diet based on a lot of fish and rice and such. So when you're coming out with dietary action levels, here's the general makeup of what a young child would be eating, age 1 through 6. And we could develop PFAS action levels for every individual food group here. But a simpler way to do it just to start is just think about the total amount of food the average child is eating. And by the studies here, we say 563 grams of food per day. The same child will be drinking 0.78 liters of drinking water and soil, eating 200 milligrams of soil. It's a small pinch. So somehow we have to distribute the daily PFAS dietary uptake among these 3 different types of media. So we already talked about having a relative source concentration or relative source contribution of 20% for soil and water, kind of combined. We have to think about that more. For food, we'd assume the other 80% of the PFAS that we're being exposed to are in the food in this 563 grams. A lot of ways to do this. It's just one example. So here's some example PFAS, what we call whole diet action levels. Just think about this, say for your octosulfonate, if you just look at based on the toxicity factor, your total average daily dose allowable would be 300 nanograms per day. Well, we're going to assume an 80% relative source concentration contribution for the dietary exposure. And then again, it has a quotient of 0.5, so 300 times 0.8 times 0.5, the target average daily dose for dietary exposure, 120 nanograms per day. We know that child on average is eating 563 kilograms of food a day, so we just take the average daily dose divided by 0.563 kilograms per day, and we come up with a food action level for PFOS, as if you put all your food in one big blender, of 213 nanograms per kilogram. This would apply to any of the food groups in that blender, a single number. Again, just for example, there are different ways to do this. You see the action levels, whole diet action levels for all these other compounds. PFBS, not very toxic. But then you get down to some of the longer chain compounds that are more toxic. You'd have much lower action levels for food. Back down into the parts per trillion. So that's the food action levels are pretty simple. Let's back to this example. What's the target action level for PFOS in corn? Go back to the action level we just discussed, developing 120 nanograms per kilogram. Let's just assume that. So the main thing we need now is the bioaccumulation factors for soil and groundwater. What concentration of PFAS in soil would yield a concentration in corn of 120 nanograms per kilogram or less? The same thing for groundwater, irrigation water. Well, these we don't have a clue on. We haven't looked at this at all. We've looked at some published information. The published bioaccumulation factors tend to be highly variable within and between studies. Well, the variability, there's a lot of factors could lead to that, including the soil type, the microbiome in the soil, between different fields or even within individual fields, the specific plant species, what type of corn are you talking about, fertilizers, lots of complicating factors. Anytime we see highly variable data, if you're familiar with the work our office has been done over the last 15 years at all, the first flag that comes up is you weren't collecting the samples properly. So we're not going to spend a lot of time on this, but likely another problem in these studies is they were using discrete type samples where you collect a random sample of soil from, say, within a field and a random plant and testing that and assuming that's the bioaccumulation factor. But that doesn't really work. You have to collect multi-increment type samples. That's what I want to end up on the last part of the presentation is how do we get representative data, especially for these bioaccumulation factors, even when we're investigating sites and doing risk assessment. So again, we've been working on this for 15 years. We started working with a bunch of farmers and we got in touch with a bunch of miners, and they would never do what we've been doing in the environmental business for 30 years, grabbing a random handful of dirt, putting it in a 4-ounce jar and handing it to a lab and let them test a random pinch of that. And this is a field study we carried out several years ago. We went to 3 different sites and collected hundreds of side-by-side discrete samples just to get a better idea of just how random and variable can concentrations be around a single point or within a single sample. So at each site we designated 24 grid points. You see these are fairly small areas. I think the largest is about 5,000 square feet. Arsenic site is a soil contaminated with wastewater containing arsenic, so we expected the variability to be fairly low or lower than any other site. And the average variability between co-located points, about twofold. It's 120 ppm here, 260 ppm right here. We saw the same magnitude of variability even at part Berbian level. So from a field standpoint, this isn't that bad, only twofold variability, but talk to a risk assessor. Is it 120 or is it 260? What if your action level is 200? Well, that's exactly what happened at the lead site. At this site, we were looking at incinerator ash that was mixed with soil used as fill material. Incinerator ash had lead in it. Here, we thought we'd see high variability, and that's exactly what we did see. Average total variability between co-located samples and within individual samples, like how much air could you get in the sample, is about 7-fold. So 120 ppm here, and then just a foot away, 800 ppm. The interesting thing at this site is that our action level in Hawaii for lead is 200 ppm, and every single grid point, all 24 grid points, we could collect a discrete sample that was below 200 and above 200. So someone could go to our lead site, collect 24 samples, and they all come up below our action level, 200 ppm. Somebody else could go back the next day in essentially the same spot within a foot or two, collect a sample, and they'd all be above our action level. So start thinking about that in terms of what that means in the field and why it takes us years and years to investigate a site. With a PCB site, we thought would be the worst, and it was the worst. Is PCB data tend to be all over the place. So this was the worst spot where we had one sample, discrete sample, 4.9 ppm, and then right beside of it was a sample of 2400 ppm. So it's that 500-fold difference or something. So it just tells you how random the concentration of a contaminant is in a discrete sample is based on where you collect that sample. Average total variability around individual grid points about 39-fold. That's why it takes us so long to clean up PCB sites and all these sites in reality. So a key point, the data for discrete sampling points in means, we'll look at in a minute, for multiple points are random within a largely unknown range. Maybe it's twofold, maybe it's, who knows, 10-fold, 100-fold. Twofold is probably the best you can do. So it has a lot of implications for risk assessment, getting back to that, and we start looking at bioaccumulation factors and uptake into plants and such, is at these same sites, we went back and we collected essentially replicate data sets. Imagine going to the same site, collecting a set of 10 discrete samples, calculating a mean, and we went back and did it 20 times. 20 different people went there. Well, guess what? You get 20 different means. Here we're just showing the 95% UCL, but the means had the same variability. At the arsenic site, the mean only varied by a factor of 2. But tell that to a risk assessment who thinks the 95% UCL is telling you something about precision. Well, it's not at all, because it doesn't take into account sampling error. The lead site was getting worse than that. Now the means are varying by a factor of more than 2. This is only for a few sets of 10 samples. And then the PCB site, the mean, depending on which group of those 10 random discrete samples collected in there, you could see just was outrageous when you calculated 95% UCL, totally random. So a key point here is the mean for a single data set is random within an unknown range. That's why your bioaccumulation factor studies, you have so much variability in the data. At least that's part of the issue. So sample collection error, that's the problem, can't be estimated. And the estimated mean can't be quantified. So you have no idea really what the error is in your data and in your estimation of a mean when you're looking at a single set of discrete samples. You'd have to collect multiple sets, and even then it may not be correct. Something a statistician pointed out to me, we work with a lot of international sampling statisticians now, especially in mining companies and agriculture, is that statistical analysis of a single data set only evaluates the precision of the statistical test employed to estimate a mean for the data provided. It doesn't tell you anything about total error in that sample. So this can really yield a false sense of data precision, either in risk assessment or in these accumulation factors and such. So it's a pretty simple solution, and this is what the farmers and the miners have been doing for decades, and risk assessors should be doing. I should have been doing this 25 years ago. So the question from risk assessment standpoint is always, what is the true concentration? What is the mean concentration of the contaminant in the targeted, what we call decision unit, like an exposure area, and volume of soil? It could be sediment, air, water, food, whatever. You designate an area and volume of your media, and you collect a representative sample from that. So for soil, the way to do that is you collect a single multi-increment sample by combining 40 to 20 gram increments of soil from 30 to 75 points. Our default is 50 into a single sample. You want that total sample mass to be about 1 to 2 kilograms. There's a ton of science behind this that the mining companies and agriculture people have been working on for decades on why this works, and looking at, they have a lot of databases. They've done a lot of statistical analysis stuff. But that gives you a pretty good answer. So when you collect this sample, then the sample has to be carefully processed and subsampled at the laboratory. And you would collect plant samples here. Let's say these are melons. We want to know what the bioaccumulation factor is. We'd collect a 50 increment, multi-increment sample of the soil, 1 to 2 kilograms, and then we'd collect we'd get about 50 melons or something ideally in here, and collect part of them anyway. And there's our one sample of melons, and we get concentrations, compare the melons to the soil, and there's our bioaccumulation factor, or the soil to the melon, however you do it. Well, how do we know that's right? We're going to go back and do it 3 times, 2 more times. So we have 3 samples of soil, 3 samples of melons, all independent. And we can look, then we can start looking at total precision in the data, which we could never do with discrete samples. So it's really fun when you start doing this in the field. We have a lot of guidance published on our webpage, sections 3, 4, and 5 of our technical guidance manual, first published in 2009. We just updated a few years ago. We have lots more updates. Our office is kind of unique. We do a lot of our own field work. So we come up with great ideas in the cubicle and then go out in the field and realize how they don't work or they do work. And we work with a lot of consultants here. We published a paper on the study I mentioned on discrete samples, a critical review of discrete soil sample reliability, 2-part paper you see here, first on the field results, second on implications, site investigation, and risk assessment. We also have a lot of training webinars posted to our webpage, including a webinar we gave to the State Risk Association last July. If you really want to know about sampling, then this is the guy to talk to, Chuck Ramsey with Envirostat, formerly with US EPA. He's kind of the US guru of sampling of everything. So all the staff in our office, or most of them, have been taking this 4-day training class, as have most of the consultants in Hawaii. This is similar to ITRC's ISM document. Probably a lot of people have heard of that. On the mainland, you hear the term ISM. So that's a great document to start with. And one thing to understand, though, most of the people that wrote that initial document, only out of 100 people on the team, only 3 or 4 or 5 of us actually had any training in sampling theory or even field work. So there's a lot of gaps. And the updated document is going to be coming out soon. It's going to have much better information on field implementation, but there's still some issues. There's a group that still insists that discrete samples are the gold standard, but they don't have a good training in it and understanding this issue. And I think that's going to get, unfortunately, put in the updated version. But something to think about. The best way to understand this is go out in the field and start collecting samples. But the same problems I mentioned in the presentation I gave with the State Risk Assessor group this time, we see in a lot of environmental data. In the bioaccumulation, food uptake data and the soil sampling data. You see the same thing in soil vapor data. We realized we started looking at vapor intrusion risk, which is something else we've been looking at for the past 20 years. So one thing we realized several years ago, the US EPA has published their empirical database for vapor intrusion, where they went out to hundreds of homes and buildings, collected a sample of indoor air. We have webinars on this. The indoor air people really know what they're doing. They're far ahead of any of the rest of us. But then they collected a single sample of soil vapor directly under the slab. But when they did that, they only collected a small 1-liter sample. So the indoor air and subslab vapor attenuation factors published in that database, they're based on collection of a single 1 to 6 liter vapor sample beneath each building slab. Here's from the paper we published. You see reference down here. Think about this. These X's could be individual discrete soil vapor samples. But if I collected a sample here, I'd get a very different attenuation factor than if I collected it here, where it's really high concentration, low concentration. So these attenuation factors are totally reflective of where you happen to collect the sample. So if you went to another point, you get a different attenuation factor. There's no way to fix this problem. So in the end, the database isn't scientifically defensible or even for use for development of generic attenuation factors. You can't fix it by statistical analysis. That's a big myth that a lot of people in the environmental world, including me early on, had. Well, just give me a bunch of data. If a lot of it's junky, then I can run it through a pro UCL and I'll get a right answer. But think about it in terms of, I mentioned in the presentation, all the people in the webinar that joined in, I think 120 people or so. What if I picked 20 people at random and I wanted to get the mean age of the group? So I asked the 20 people at random what their age was. Well, I can calculate a mean, I can do a 95% UCL and such. But then I found out later that a lot of the people, if not all, lied about their age, or they just made a number up. Well, what can I do with that data? Nothing. Really, you have to toss it and start over. You can't just plug it into a database and think, or a statistical test and think that's going to solve it. So that's a big issue. So one thing we point out with the US EPA vapor intrusion database, it's a useful, but it's a failed scientific study. We've been pushing to remove that for years from the guidance. Maybe one day they will. You see the paper we published down here. That we rant and rave a lot about it because it causes the same problem as discrete soil samples and bioaccumulation factors. The subslab attenuation factor that they erroneously, I'd say, extracted from the database at 0.03, flags lots of really low risk sites, and it's causing a lot of damage to small businesses and property owners. That shows up in political situations, which we're dealing with now in 2020, I think. So we really have to focus on good science. And our group loves to debate science, and we're more than happy to admit that we're mistaken about something and learn to move on. I think this is one issue we're on the right track on. So a better way to do soil vapor, collect soil vapor samples. Same thing as if you're collecting food crops or soil from fields or soil in general, you need to collect a really big sample. And you need to designate the volume and area of the media that you want to sample from, and you need to go get a representative sample from that. So we also have guidance on what we refer to as large volume purge sampling methods, which Todd McAllery with Geosyntec and other people have been doing for years, but the environmental world is just catching on to in general. And here we go to a single point in the slab of a building, a hypothetical vapor entry point, and then we're going to purge the volume of vapors that hypothetically could get sucked through that point based on the pressure differential in a single day. And we're going to collect a single sample of that purge, these 2 canisters here, as it's being purged from the vapor point. We're going to do that 5 times to simulate 5 days of vapor intrusion through that point. We did this, the field study we did, you see the sample data here. Same thing we see when we're doing multi-increment samples for soil. The bigger the sample, the higher the concentration. So these are 7,000 liter purges through that vapor point. You see the concentrations going up, up, up. That's because as we purge more and more from here, we're starting to capture these little isolated hot spots of vapor under the slab that chances are you totally miss with your discrete soil vapor samples. So we get a higher concentration. This is still just hypothetical risk. We don't know that the data we get from this point here is reflective of vapors that could actually be intruding into this building. And this was actually a former dry cleaner. The building's gone here, obviously. But it still gives you some better idea of the potential risk could be post and vapor intrusion. So you see it's in our guidance manual here, section 7. We have several webinars published on this. So that was it. It's just a quick summary then. Now we have action levels for 18 PFAS. We're updating those to reflect the anion forms of the chemicals, their fate and transports to the acid forms like we mistakenly did in the July document. This significantly expands guidance in general. And again, it's just a compilation of lots of states that we were able to do here. And we can more reliably screen our PFAS sites now for potential environmental risk instead of just looking at PFOS and PFOA. We could miss problems. Now we can look at the full suite of common chemicals, compounds we're finding. Some of the lingering concerns, leaching from soil, impacts to groundwater, really have to move to laboratory-based tests for that. The SPLP leaching procedure or better, we need soil column test, come up with a faster, cheaper way to do that, which we're working on. But then the big bugaboo is this uptake in edible plants from fields and in with biosolids. We're talking about several million acres in the U.S. or irrigated with treated wastewater. Our guess is that, and really we have no idea, but that's our guess, is that in most of the cases it's not going to be an issue, because I'm sure people are looking at that now. We haven't heard much about it, but in a few cases it will be, and that's where the fields were getting biosolids or wastewater from wastewater treatment plants that received a lot of their wastewater from industrial sites that were using PFAS in their process, or actually developing them there, making them there. So we'll post our updated action levels sometime in the next month or two, and hopefully we'll start undertaking some plant uptake studies next year. We want to coordinate with other states on this. And then also we're looking at better ways too, looking forward to doing this at ag fields, is better ways to collect representative soil and plant samples to look at biouptake factors. So that's it, and we'd definitely appreciate all the people joining in. So we love to chat here in our office with anybody who's interested in talking about anything. We love to debate issues in a good, fun, professional way. So you see my email here. So get in touch, and thanks again. Mahalo.